Okay, in this video I'm going to continue on with my tutorial videos on thermodynamics and statistical mechanics. This is video number 14 and I'm going to get the Taylor and MacLaurin series expansions for 1 plus x to the n. So in the previous video, which is on the Taylor expansion, or I call it sub-video Taylor 1, we got the following formula for the Taylor series. And we know that in order to go from the Taylor series of f of x to the MacLaurin series of f of x, we set a, or where it's centered at different places. So we set it at a is equal to 0. So really the difference between the Taylor and the MacLaurin series is that the Taylor series can be expanded anywhere we like, or centered anywhere we like. That's supposed to be x is equal to a, whereas the MacLaurin series must be centered at x is equal to 0. That's the difference between the Taylor and MacLaurin series. So let's go ahead and do this. So just a quick reminder, it's in the formula here, but in order to get it, so we'll say what I am outlining here, they are the coefficients in our power series. So in order to get the coefficients, we need to get the n derivatives in our function. So, well, the 0th derivative is just going to be the function itself, which in this case is 1 plus x to the power of n. The first derivative is going to be equal to n times 1 plus x to the n minus 1. The second derivative is going to be equal to n times n minus 1, 1 plus x to the n minus 2. The third derivative of x is equal to n minus 1, n minus 2, 1 plus x to the n minus 3. Note here, this n is equal to 0, n is equal to 1, n is equal to 2, n is equal to 3. Alright, so where do we go from here? So, get rid of that. In actual fact, just for argument's sake, I'm going to write it like this, so it's even more clear. Now, although we're not going to calculate it in this way, just to show you that the coefficients are correct. So I said this would be coefficient 0, 1, 2. Well, it's going to be n minus 1. Actually, sorry, I haven't got my coefficients yet. But look, in order to get them, we need to evaluate our n derivatives centered or evaluated at x is equal to a. So now, before we go any further, we need to get rid of x, because that can be any place, and actually pick a spot where we're going to evaluate it. And we're going to evaluate it at a. Like that. That means that, let's say we take this particular coefficient here, so it's 0, 1, 2, the third coefficient, c sub 3, is going to be equal to n minus 1, 1 plus a to the, that's a now, n minus 2, and we need to divide by 2 factorial. Pretty straightforward. Or in this case, this would be the fourth coefficient, so it's going to be n minus 1, n minus 2, 1 plus a to the n minus 3 divided by 3 factorial. Now, we don't actually plug these into the, we don't plug them in that way, but anyway, let's go ahead and now calculate the Taylor series proper. So we have each of those coefficients, and we multiply it then by x minus a to the n. So that means that the Taylor series, or the Taylor expansion of 1 plus x to the power of n, with each of my coefficients, as I said a moment ago, multiplied by 1 minus a to the n. So what were the first was we had x minus a, what am I doing? 1 minus a to the n, that was c sub 1. Then we had x minus a to the 0 divided by 0 factorial. Sorry, this should be 1 plus a, because this is our function here. Okay, next we have n, then we had 1 plus a, the n minus 1, x minus a to the power of 1 divided by 1 factorial. Then we had n minus 1, 1 plus a to the n minus 2, x minus a to the power of 2 divided by 2 factorial. and just I'll do one more. n minus 1, n minus 2, 1 plus a to the n minus 3, x minus a to the 3 divided by 3 factorial. So if you add them all up, you get your Taylor series. So let's go ahead and get the MacLaurin series. So the difference here is we just set a is equal to 0. So if we set a is equal to 0, I'll let you do it yourself, but we find that the MacLaurin series of 1 plus x to the n is equal to 1, so it's 1 plus n to the, we have 1 to the power of n minus 1, we have x and we divide it by 1 factorial, we have n minus 1, 1 to the n minus 2, we have x squared divided by 2 factorial, and so on. Now look, I just plugged in the figures. It's very straightforward, obviously, so you can do that if you like, or you can accept it. So what happens if we set a power of n to the half? Let's say n is equal to half. In other words, I want to get the square root of 1 plus x, or 1 plus x to the half. Let's say if I want to get the square root of something. So that means we need to set n as a half. And if we set n as a half, we're going to get the following. We're going to get 1 plus x over 2 minus x squared over 8 plus, and off into infinity. But like I said, the more terms you add up, the more exact our expression becomes. But if we just took the first two terms, we get that the square root of 1 plus x is approximately 1 plus x over 2. The square root of 1 minus x, of course, would just be this. Now that is where we took the first two terms of our expansion. When can we take the first two terms of expansion? We have 1 plus or minus x to something small is approximately 1 plus or minus x over something small. And this is the Taylor expansion I'm going to use very regularly. It's used all the time in physics. So, sorry, this is the MacLaurin expansion of the MacLaurin series. So 1 plus or minus x to something small can be approximated as 1 plus or minus x over something small by taking the first two terms in our MacLaurin series. So, thanks for watching. Please pass it on to your friends, subscribe to my channel, and also, if you're in a good mood, you might click on an ad. Thank you.